Okay, assalamu alaikum viewers, and in this tutorial we are going to discuss the concept of integration involving just single variable function, or what we say a univariate function, as you can see over here. So before moving ahead to the examples of integration and the types of integration, just understand what exactly the geometrical interpretation of integration is, and what integration, how integration actually helps in practical lives. What is exactly its significance? And you know that integration is one of the indispensable content of our in the field of calculus, right after limits and derivatives, I mean. So over here, in order to understand the geometrical interpretation of your integration, I just assume that let consider any function, we call it f of x, and once when we plot it on a graph paper, it gives me a curve like this, just for an example. And then I'm going to restrict this curve with respect to a certain interval from A to B, like this. Okay, I have just restricted my this curve with respect to a certain interval along the x-axis. Okay, you call this interval as A and B. Okay, I've just restricted this curve within this interval, and my objective is to find out the area under this curve. So how I'm going to calculate the entire area so occupied under this curve within this limit? So what I have to do, how about if I simply divide this entire region, this entire area under the curve within these limits in some particular quantity of rectangles, particular number of rectangles having same width. Okay, so in the beginning we are going to draw we are going to divide this entire region in n number of rectangles having same width, and it appears to be like this. And if the width is quite sufficiently large, then in that case I'm going to have a case like this, you can see. Okay, so this is it. I have just divided this entire region under this under the curve within this interval in some particular number of rectangles, and each rectangle is having same width, you can see, and I just name this width as my del x. Okay, and you can see that if I just take my x equals to A, then in that respect the projection is falling on the curve over here, and in this way I can easily trace my y coordinate, which is said to be my f of A. Okay, in the same way, if this point is your x1, okay, this point is your x1, this point is your x2, this point is your x3, this one is your x4, this one is your x5, and this is your xb, and you call it xa. Okay, this is it. And the difference, or the width between in the first rectangle, you just call this width as your del of x1. The width of this rectangle is named as del of x2, and so on. Though the values of all these widths is same, but we have just made a distinction in their representation, in their notations, I mean. So it appears to be something like this. Okay, I hope you've understood this thing. So now you see, once this is your x1, okay, this is your x1, in this respect this point is just touching the curve right over here. So with the help of that, I just come to know that this point is your f of x1. Okay, and so forth, you just keep on calculating your f of x2 and so on. So in this way I can assert that if I talk about this rectangle, the area of this rectangle can be determined by multiplying its width with its height. Okay, so the area of this first rectangle, let us name it rectangle number 1. So area of this rectangle is the product of its width del x1 and its height, which is f of x1. Okay, so my area 1, for example, the area of my first rectangle, let it name it A. It is the product of your f of x1 height into del x1 width. Like that, you can keep on calculating the area of all these remaining rectangles. So actually now presently, once when I sum up all the areas of these rectangles, I'm going to get area under the curve. But not only just area under the curve, I'm having these extra portions also. Okay, so this is bringing some error in the area. I'm not getting exact area that like I should get with it, which is just the restricted within the under the curve and within this interval. So I'm having these extra regions as well, so I have to minimize this error. So what should I do? So I'm having a solution over here to minimize this error and to ignore this thing. What is that? If I just divide this region under the curve within this interval into a rectangles having width del x much smaller than this one presently that what I'm having. Okay, so I just minimize my width of the rectangles, means I'm going to increase the number of rectangles now, and it's possible only once when I minimize the width of the rectangles. So once when I minimize the width of the rectangles, this is going to reduce the concept of error over here. Okay, so let's see another figure related to this. So it comes over here. You can see it is. Okay, so now you can see here that I have just minimized the width of the rectangles, and you can see now the concept that the presence of this extra region is now getting minimized. So once when I keep on further reducing the value of the width of my rectangles, it's going to increase the number of rectangles, and along with that it is going to decrease the error. So once when I just minimize my rectangle up to infinitesimal extent, means if my del x approaches to 0, so in that respect I'm going to have infinite number of rectangles, and those rectangles are not going to exceed this curve, they will be within this curve, and in this way I can obtain the area under the curve entirely by summing up the areas of all those individual rectangles which are infinite in numbers. Okay, so now let us now write down the area under this curve as the summation of all these infinite number of rectangles when my del x approaches to 0. Approaches to 0 doesn't mean that del x is equal to 0. It means del x is getting so small that you cannot even count the value of this del x, and it is extremely small, so small that it is very you can approximate it to 0, but basically it is not 0. Okay, so that's what this notation of limit explains you. The del x is approaching to 0, but it is not 0 actually. Okay, so now let us write down the area under this curve is expressed as the summation of infinite number of rectangles. Okay, so let me write down the expression for this purpose. Okay, so that's how the area under this whole curve is actually the summation of the areas of all the individual rectangles present within the curve. So you know, I have just explained at the back that area of each rectangle is so obtained by multiplying the height with the width. It's a basic formula of finding out the area of rectangle. You know that, something that you study in the primary classes. So you see, in every once each rectangle is having extremely negligible width, so I have just applied here the limit explaining that the width is very negligible and is very infinitesimally small, so del x is approaching to 0. So that's how you just write down the area of the first rectangle plus area of the second rectangle, and so on up to the areas of infinite rectangle. You sum up all these areas. Now you can see with every area you're having the limit attached, you can take it out common. Okay, so once you take it out common, it looks like this. Okay, that's how it looks like. Now I'm not in mood to write all these notations again and again, so how about if I generalize and apply the concept of summation here. Okay, I just apply here the concept of summation. It is a Greek notation, and I is going from 1 to infinity, f of xi. upon del xi. That's how I have just enclosed this entire big thing in this form. Okay, so you see, once a limit is over here, it is covering every even the minute intricacy in the calculus. So once when the limit is applied here and the summation is here, now this summation, because of the limit, is going to be transformed in this elongated s. Okay, elongated s comes from the for the summation sense, and this is the elongated s telling you a big summation and integration concept. Okay, this f of x will be written in the general form, and this del x will be transformed in d of x. So that's how, and the interval limit a to b is going to be expressed like this. Okay, so this is something that you call the Riemann sum. The Riemann sum, we just call it a Riemann sum. And Riemann sum is explaining how the concept of integration arrives. Okay, so you can see here that integration actually helps once when you are talking about just a univariate or single variate functions. The integration helps you in determining the area under the certain function curves. Okay, and once when you move on in advanced calculus, in advanced integration, in univariate up to multivariate, you talk about your double and triple integrations. Over there, you not only discuss the areas of under the curves, you also discuss the volumes of the certain plane within the 3D space. Okay, so that's how, and then you move on to the in calculating the volume of the solid revolutions and all that. So this is just a primary approach of understanding what exactly an integration is. So on the basis of this concept, you just strive the basic formulas of the integration that is chiefly provided in the classes, the students easily, and you also have that thing. So how those formulas are arrived, this is at the background, this theory is running out there. Okay, so this is what exactly an integration is. Now once you're having the basic formula sheet in your hands, with the help of that you are going to solve the questions which are given to you in the assignments. All right, so now move ahead and let's discuss a few questions present in your assignment. Okay, here you go. The second question of your assignment is mentioned over here. So this is the function that is written right after this elongated s. This function is called the integrand, and this is a function involving just one variable. This is a univariate function, you know that. So this function contains two terms over here. One term is this, another term is this. So how about if we just write both these terms in individual integral form like this? Okay, so you can see here that in the first integral, in this integrand, you're having a constant number 3. So always take out the constant term outside the integral sign. Okay, and over here, how about if I just replace this radical with its power? It becomes easier for me to handle then. Just like that. Okay, so over here you can simply apply the formula of your integral of xn that is mentioned in your formula sheet, and it is actually n plus 1 upon n plus 1 plus some constant. So you can apply this formula over here in this part. But what about this? Okay, so basically this thing can be done directly, but in order to understand in order to saturate yourself to a very good extent, how about if I just suppose that let this f of x, 5x plus 2 is equal to some variable. If I just assume it, that let 5x plus 2 is equal to some variable, let it be 1. Okay, then you just derivate both sides with the help by means of your original variable x. So once when you derivate both sides with respect to the original variable x, you're having this. Okay, so you see, just apply the derivative of differential operator individually in both these terms. It's going to be written like this. Okay, so you can see that the derivative of x with respect to the x is 1. So let me write below. So it comes out to be 5 into 1. And remember that the derivative of a constant number always comes out to be 0, because the rate of change of a constant thing is nothing but 0. So this is a constant number 2, so the derivative of this thing is definitely 0. So this is it. So dy by dx will be written as it is, because y is totally different variable with respect to the variable involved in this differential operator. So it cannot be derivated, that's why. So that's why it is written as it is, okay? Now over here, you're having just 5 left here, and it is dy by dx, okay? So you need to compensate dx as well with respect to the variable y. So once you are replacing this 5x plus 2 by means of y, so this dx cannot be written right after that. We have to replace this d of x as well with respect to the y, d of y. So dx is equals to what? Over here, this thing interprets this once when you shift this dx over here and 5 over here. So you can say that dx can be replaced by 1 upon 5 dy. Okay, so now this work is going to be used here. You're going to use y at the place of 5x plus 2 and 1 upon 5 dy at the place of your dx in this part of integral. Okay, so you can now easily handle this thing. So let us apply and let us do the work. So integral of your 3x squared minus under. Over here, we were simply using the formula because it was quite easy to handle for us. So it is, that's it, minus integral. At this place, you're going to put y power half. Just going to put y power half at the place of your dx. You're going to put this, okay, d of y. All right, and this constant number is now going to be written outside the integral right over here in the next step. Okay, so that's how thing looks like. So you see 3 and 3 gets cancelled and you are having x cubed here just, and over here once again you can see that this is an integral of some variable power having some power. So you're going to insert once again the formula of your xn here. So the integral of xn is xn plus 1 upon n plus 1 plus some constant, because you are not having the limits in the integral. This is an indefinite integral, that's why. So whenever you are dealing in indefinite integrals, you're not having a limits there. So in order to put the compensation, you put constant at the end. Okay, so now simplify. So once you take out the LCM, it gives you 3 by 2. I hope I do not need to do that basic thing for you. You're good enough to handle, I hope. So this is it. It's 1.5. This thing will get in over here. You are going to take the reciprocal. It is going to be inverted. So 3 by 2 plus some constant. So x cubed minus 2 by 15 y power 3 by 2. Okay, and you know that previously you were taking what? You were taking the y was your 5x plus 2 up there. It is 3 by 2 plus, and you have just restored the original variable at the end, and this is your final answer. Okay, so that's how you do. Now I hope that you have understood this problem. Now move ahead to the next question. Okay, so this is your question number 4 of the assignment, and I hope you can easily handle question 1 and 3 likewise. They are similar. So you can see this is the integrand over here. So how about if I just divide all the 3 terms present in the numerator by the denominator value, which is just x power half. So I have just written this thing like this, okay, and then I have divided this x power half with all these 3 terms present in the numerator, okay, and that's what it looks like. Now you can see that you are having like variables, so once when the denominator powers goes upwards in the numerator, sign gets changed. Okay, so that's what we have done in the next step. The signs have just gone changed. Okay, then you simply resolve the powers. You just take out the LCM, you simplify, it looks like this. Okay, and then the final answer, the final term, the simplified integrand is now appears to be like this. Now you're going to apply the integral individually on each term present in this integrand. Okay, so that's how it looks like. And as I told you in the beginning, that constant number of the integrand is always written outside the integral, or always written before the integral. Okay, now over here you can see that this is the integral of the form of xn. Once again, you just apply the formula of your integral of fxn dx, and it is xn plus 1 upon n plus 1. So we have just applied here this formula. Let me write it again for you. X power n plus 1 upon n plus 1 plus constant. So this is the formula that you are going to apply in all these three integrals. Okay, so it looks like this. So that's how a thing appears to be. And then you talk about the denominator, which is here in the form of fraction. So once it gets inverted, it looks like this. So you see, finally, the answer of this question is this. That's some constant. So that's how the integral has been, that's how it is resolved. Now, as far as the other questions concerned, they will be solved in the next video. So keep watching.